семинара. Начнем работу. Значит, перед вами выступит профессор Ки. Он представит, значит, свой доклад.
Thank you. So first of all, thank you very much for the kind invitation to give a talk in this prestigious university. So this is the first time I'm giving a talk here, so I'm very honored. So before I start, well, I have to say that there is not going to be much mathematics. There will be some, and of course, there will be some equations that some of you are familiar with. But what I want to show in this talk is, well, I've been studying water waves for more than 20 years now, and from a mathematical point of view. And then, we have the ocean. So then, is there, what is the link between what we do from a very fundamental research point of view on the water wave equations and what we can observe in the ocean? And and also I have a PhD in civil engineering, so I've always been in touch with engineers. So here I want to talk about the formation of rogue waves, and of course I will try to give a definition, if there is a definition. And so I want to start here. So this picture here, it was given to me recently by François Sarano, who was the former scientific advisor to Captain Jacques Cousteau. You might have heard the name. And actually, François Sarano was involved in a very nice movie that came out a couple of years ago. It's called Oceans. So I don't know if you've seen that movie. But I met him last month, and we were talking about rogue waves. And then he said, "Oh, but during one expedition, I took a picture of a wave that could be like a rogue wave. So I haven't defined what it is, but for now we can say that it's an extreme wave. And so this is a nice illustration here of such a wave. So the picture was taken near the Kerguelen Islands. And also, so the formation of rogue waves is a new project that was recently funded by the ERC as an advanced grant. So together with Professor John Dudley at the University of Franche-Comté in Besançon in France, who is an expert in lasers, in nonlinear optics. So in a few minutes you will see the link. Why am I together with a physicist in optics to study rogue waves in the ocean? So, what are rogue waves? They are large oceanic surface waves that represent, so there are now some important words from a mathematical point of view, statistically rare wave height outliers. So the wave height, for those of you who are not familiar with water waves, the definition is the height from the crest to the trough. So actually I like this illustration, which is an old illustration, 1934. Now, this is the first difficulty. There are, well, fortunately, very rare events. So, well, if we want to understand them, it's not so easy because we don't have that many observations. Actually, we have very few observations. And so there are a few that people in the field use on a regular basis. So that's one of them, February 86. It was a nice day with light breezes and no significant sea, only the long swell, about 5 meters high, and the wavelength about 200 to 300 meters long. we were on the wing of the bridge with a height of I of about 17 meters. So it gives an idea of the height of the wave. And this wave broke over our heads. And so this shot was taken while the ship was diving down of the face of the second of a set of 3 waves. So actually there are a number of interesting words in this statement from the captain of the ship. And so, well, and of course from an engineering point of view, why do people care about these waves? Well, they can do some damage. And so here, for example, the foremast was bent back about 20 degrees. But so what is interesting is no significant sea. So it's not like you are in a storm. The sea is relatively quiet, but then you can have some very large waves. And then the other important is the second of a set of 3 waves. So you will see that, well, in the theory we'll present later, you will see that, you know, it's quite plausible to have, well, it could be 1, 2, 3, but usually no more than that. So what's the definition? Well, there is no definition, but so we have to use one. And the one which is used, and it's not satisfactory, it's the wave height is more than twice the significant wave height. What's the significant wave height? It's the average wave height of the 1/3 largest waves in the ocean at given time. So and some people use 2.2, but we'll use 2. In any case, it's not a very precise definition. So essentially, you are in a sea state, and the significant wave height is 10 meter. Then we'll say we'll have a rogue wave if you get a wave of 20 meter. So now, this sentence here is probably the most important one of the talk, and you will have to remember this later. These waves are localized both in space and in time. So that's really important. Well, that's why, you know, it's not so easy to find them, because it's so localized. But so it's not like a regular swell. It's not a periodic wave. It's really a phenomenon which is localized. And just to give an idea, I put the order of 1 kilometer square, I would say. So that means that 2 of you are in 2 different ships, and the ships are 5 kilometers away. One experiences a rogue wave. It's most likely the other one will not experience the rogue wave. Same thing for the time. If you go through the same spot exactly, 5 minutes later, most likely you will not encounter the rogue wave. So now, of course, sometimes there are some extreme wave events, and so do we believe the people who mention these events? So really, the first, when people started to say, well, these waves really exist, it was this, well, there have been some other measurements, but this one was really nice. It was on January 1st, actually, of 1995, on a platform on the North Sea. And so here, that's the elevation of the sea surface in meters. That's the time in seconds. So I blew up the numbers so that you can see them. So here, it's 10 minutes. From these 2 sides, and then the elevation, that's 20 meter here and minus 10 meter. So then on that day there was a significant wave height of about we'll say, well, from 5 to minus 5 to 10 meter, and then there was this extreme wave here, so from about 18 to minus 7, so 25 meter. So that's really a very nice observation. But again, we have very few of these. So how do you understand a phenomena where you don't have that many observations? So recently, last year, Nikolkina and Didenkulova wrote a paper, which is a catalog of rogue waves in the 5 years between 2006 and 2010. And what is interesting in that paper is that they suggest that rogue waves occur not only in deep water, but also in shallow water and along the coast. So, and then of course, along the coast it's much easier to spot these waves as opposed to the deep water. So the fact that there are few events in deep water does not necessarily mean that there are more rogue waves in shallow water, but in any case in this catalog, so there were 9 events in deep water, 30 in shallow water, and 39 along the coast. Among the most recent manifestations of these waves, there was a surfing competition in Maverick in the US in 2010, and then so all the people were there to watch the surfing competition, and then suddenly a rogue wave came. And this one was a cruise ship, the Louis Majesty, and it was in Spain, and then it was hit by a rogue wave. So actually the wave came all the way to this level, then broke all the windows, and so what you see here is all the furniture that has been taken outside, from the inside, and well, 2 passengers were killed during the flooding of the ship inside. So I've been in touch with some passengers, and well, it looks like the captain was going too fast. So that, well, that's more now from a practical point of view. You know, there are rogue waves, but if you face a rogue wave, then probably you should slow down. But that's another story. So if we go to shallow water, well, we can still use this definition of h more than twice the significant wave height. What about rogue waves along the coast? One possibility is to compare the run-up. So what is the run-up? When a wave comes on the shore, then the run-up is the vertical elevation of the wave. So then we can compare the run-up with a significant run-up, but again, even for that, there are not much data. So what we'll say is that a rogue wave along the coast is a wave that is either unexpectedly high or causes substantial damage. So, for the past 3 years, I've been based in Ireland, and so in that catalog, there was only one rogue wave mentioned, and it was in Northern Ireland. So then we decided to collect evidence for Ireland, and so together with the PhD students. And so, well, you will see what we discovered. But before we do that, Ireland is probably one of the best countries to study rogue waves. And you probably don't know that Ireland is actually one of the biggest countries in Europe. If you consider the sea territory. So this is Ireland here. So that's the UK over there. But then that's the current designated Irish continental shelf. So it's a huge area that goes quite far west with some very interesting geometry, bathymetry, with some very deep parts, some shallow parts, and so on. So yeah, this continental shelf here probably plays a role in the waves that we can have on the west coast of Ireland. And also, just aside, my other big project in Ireland is wave energy. So you probably heard of renewable energy. So one of them is waves, to extract energy from waves. And Ireland wants to be number one in Europe. And of course, Ireland has the best wave climate in Europe for that. So this is so what we found. So it's our catalog of extreme wave events in Ireland, and we tried to distinguish between 3 types of waves: storm events, so that's the green stars, so like these, Then tsunami events, so you might wonder why tsunamis in Ireland. Well, essentially, most of them were the 1755 earthquake tsunami in Lisbon, in Portugal. So this tsunami went all the way to Ireland. And then the blue filled circles, that's what we consider to be rogue wave events. Now, there is one which is really fascinating, and well, first of all, it's a beautiful area. The Aran Islands on the west coast of Ireland, so this is Ireland again, and these three islands are over there, so then this is the Atlantic Ocean. So it's getting waves directly from the Atlantic Ocean. So there are these three waves, and so this is what they look like. So very nice scenery, but very high cliffs. And actually the most interesting one in terms of extreme wave events is this part here. And this is what has been observed at several occasions. Some boulders have been thrown up during big storms. So there's a famous one in Ireland, it's the night of the big wind. Then in 1852 again, a story that 15 people were swept to their deaths by a wave. And there have been some recent studies on these boulders. So in 2004, there was this paper, and then it was storms or tsunamis. So then the authors were looking at both possibilities. And so in that paper, they show evidence of deposits on the top of vertical cliffs up to 50 meters above the sea level, weighing 2.9 tons. And then if you go to 12 meter, you find boulders of 117 tons. And if you go at sea level, some 250 tons boulders have been moved. So very energetic wave. How can this happen? So then, very recently, this paper came out last month. Then this is the title of the paper, Recent Movements Caused by Storm Waves, Not Tsunamis. So they definitely discard the tsunami option. And the main reason is that there has been no tsunami in Ireland for the past 250 years, but there has been some movements, so they must be due to something else. So, well, that's one example. Another one, so that's so already in the that's in 1885 in Nature. There was an interesting article, abnormal Atlantic waves, and so there were several ships that were hit by a rogue wave. So here I'm concentrating on these three ships here. And so in this paper, there are the dates when this happened. So here are the three ships. So one almost, well, next to the west coast of Ireland, and then these two in the middle of the Atlantic. And so, of course, this one was hit first, then that one, and then this third one. So you could think that because the three were hit, it could have been a tsunami. But now, a tsunami in the ocean is a very small wave, so that cannot be a tsunami. So what can it be? Now, I think it's in that paper that they mentioned that there is an underwater volcano there. So this could have erupted and created a wave. But I was talking to a geophysicist in University College Dublin, and he said, no, there is no known volcano at this location. So what we believe is that it was, well, a big storm. So the swell was propagating, and there were a few major waves associated with this storm. So here's the list of some of the observations. I will not go through them all, but here, that was the one next to the shore, 12-meter wave, but that's, from eyewitness accounts, so, how do you measure a wave with your eyes? It's not something easy. Then here it's 40 feet high for the same ship. And then also here, this one mentions that there was a ship next to them, but it disappeared. And then here, I think it summarizes the sea was high, but fairly true until a mountainous wave broke on board of the ship. So actually, we made a quick computation. We took the first two ships, and we have the distance, we have the time. So then we could compute the wave period, and that was estimated to be 14 seconds, and that's a typical swell when there is a big storm. So most likely it was a big storm system. Now, this one is probably the most interesting, first of all, because it's very recent. And so this is the Navy ship from Ireland. So I think it's the only one that Ireland has. And so in 2004, there was a Canadian submarine, the Chicoutimi, that was in trouble somewhere in that area. And because a fire broke out on board after a significant ingress of water during repairs. The sea was pretty rough, it was not a good day, and so actually the Navy ship had taken shelter in this bay due to bad weather when it responded to a pan-pan broadcast. So then the captain decided to respond, to leave the bay, and then when it went around this island here, then it sustained quite a bit of damage by two unusually large waves. So so as I said, there was a strong gale, heavy swell with waves approximately 3 to 4 meters, and then the captain said that the ship encountered two very large waves, 10 to 12 meters, with a short period. So actually that's the island during a nice day. So here's what happened, so we don't have to go through everything, but then a piece of the deck broke away and water was getting in, the window wipers were all removed, the flare was moving and could have built back if the ship was to continue, so the captain decided to stop and to return. Unfortunately, someone died on the submarine, but they didn't know exactly how the situation was on the submarine. I talked to the captain and said, if I'd known, I would have continued. But in any case, last week I was talking to the head of the Coast Guards in Ireland, and his interpretation is that the ship again was going too fast inside these waves. And the last example, so it's getting even closer to in history, that was last winter. So now again I insist that we have few data, and even wave data, it's relatively new. Most of the wave buoys in Ireland have been installed in less than 10 years, so we don't have that much recording. But now we have several wave buoys on the west coast of Ireland, and actually that one was moved recently. Before it was closer to the shore, now it's quite offshore, so it's about 80 kilometers to go to that wave buoy. And now this illustration here shows these big waves that were recorded. So these are the highest wave ever recorded in Ireland. So several 20-meter waves. That's over 3 days, December 12, December 13, December 14. And you have three curves. The green one, that's the observation. Now, you have to understand what we mean by observation. This is something that you can find yourself on the website of the Marine Institute. So what is provided is an hourly average of the waves, so that's sent to the shore, and then so you can find it. Now, of course, you know, these big waves, the period is typically 20 seconds. So in 1 hour, you have several of these. So what we want to really understand what happened is to get the raw data. Now, the raw data is on the wave buoy. It's collected only every 6 months. So we still don't have the raw data for this event. So I insist on these things because it's very difficult to do analysis. First, you have to wait for the data. So these are the observations. The red one is just a smoothing of these observations that we did, so plus or minus 2 hours. And then the blue one is some wave forecasting done on a computer. So that's a computer model that takes into account the wind and all the things you need to forecast to predict waves. So that's the European Weather Center based in the UK. And so these are the computations. So you see that the computations are slightly above the observations, especially when it comes to the highest wave. The simulations predicted 25 meters, and then the highest, but the highest in the hourly average is 20 meter. So now, of course, we have one set of data at a particular location in space. Now, of course, with a computer, we can cover the whole ocean. So that's what is shown here. And actually, this is where the wave buoy is. But the color code is the purple here is waves of even more than 26 meters. So that indicates that the wave buoy was at the boundary of the region with the highest wave activity. So it means that in this area, you probably got a lot of 26 meter or even more highest waves. So here we tried, but you know, it's not very meaningful to compute this wave height divided by significant wave height. And again, you know, it has to be more than 2 for a log wave. So this is the 2. So it looks like when we compute this, there is only one value which is close to 2. But again, I insist this is a 1 hour average. So probably we can say that there were several log waves on that day. Okay, so that was the introduction, but you know, I think it's important. We are dealing here with a problem where you don't have data, or very few. So what can we do? So I think now we understand how we can create these large events in the ocean. But honestly, we don't know which one happens, maybe except in a few places. And so this is why optics is going to be very important to help our understanding, because in optics you can do experiments and repeat them as many times as you want. So briefly now I go through these effects, and you see that there is a distinction between linear and nonlinear. Now, of course, these extreme waves at the end will end up being nonlinear. You have seen some pictures. Okay, so the first one is the focusing due to continental shelf topography. And the best way to illustrate this is, I don't know if any of you do some surfing, but why do surfers look for good waves? Well, they are produced by the bathymetry. There is a nice change in bathymetry that create these nice waves. So that's one effect. The second one is water waves are dispersive. So the short waves go slow, the long waves go fast. So then you can imagine, even in a linear theory, if you have some short waves, some long waves can catch up with these, and then if they all come together at a given point, at a given time, then they can just add up if the phases are right, and so you can get a large event. The directional focusing of wave train is the same type of idea, except that now you take waves coming from different directions. And again, you can imagine that waves will arrive at the same place at the same time. This one is known, for example, in South Africa. You might know that it's a terrible place for ships, and there have been a lot of accidents. So what happens there is that you get some waves in the ocean, but also an opposite current, and then the opposite current can, in some sense, amplify the waves. So these are known effects, and actually, if you talk to insurance companies, then they know about this because most of the shipwrecks happened in South Africa, and that's the reason. Now, so the ones in red, I will say a few more words about them. Now, nonlinear effects, the first one is an instability. Under certain conditions, waves on the surface of the ocean are unstable. So if some noise is introduced, then you can have an exponential amplification of this noise, and this can generate some huge waves. And then also you can find you can have the formation of quasi-localized surface states. So that's another way to create these nonlinear effects. These two are slightly related. So we come to the first slide with equations. So in water waves, we've been using for a long time now the system of equations that was introduced by Stokes. So, and Stokes, by the way, was born in Ireland. And so we consider, so that's an illustration of a Stokes wave. A Stokes wave, the name is for a periodic wave, but here I use the system of equations for all types of waves. And so we make the assumption that the flow is irrotational, and we introduce the velocity potential. So the governing equation is the Laplacian of the velocity potential is equal to 0. That's definitely not the difficulty. It's a relatively simple equation. The difficulties in the water wave problem are the Bernoulli's equation and kinematic condition. Sorry, I should have introduced a picture of Bernoulli, especially here. That's a picture of Stokes, but so then there is the kinematic condition that I didn't write down, and then which is what we say is that a particle on the water surface stays on the water surface, and then this is actually, theoretically speaking, we say that the pressure is equal to the atmospheric pressure on the sea surface. Well, actually here I've written the Bernoulli equation in the whole fluid domain. So again, that's the velocity potential, that's the velocity square, that's the elevation, and that's the pressure. And then at the bottom of the ocean, we have the kinematic condition, which is given here. So now it's this set of two boundary conditions which are nonlinear, which has produced I don't know how many hundreds of papers, including very mathematical papers on the full water wave equations. So for example, I worked for a long time with Gérard Yos, and Gérard Yos gave the proof of existence of standing waves for this system of equations, and for many, many years this proof was missing. So very complicated mathematics that can be associated to these equations. So here I illustrate three of the mechanisms. The first one, I mentioned it, so that's the dispersive focusing. And actually that's the one which is used in a wave tank. In a wave tank, if you want to create a big wave, that's what you do. So you send a wave packet, and then so these are positions along the wave tank. So your paddle is somewhere here, and that's position number 1 up to position number 8. And as the wave packet evolves along the wave tank, then it changes, and then one extreme wave, a large wave can emerge. So that's one way to generate extreme waves in a wave tank. That's an illustration of directional focusing. So I will show a movie in the wave tank of École Centrale de Nantes in France. This is an illustration of, now this is only one picture here, but this is a numerical solution of the full equations I showed here in 3 dimensions using a boundary element method. So that's very intensive numerical simulations. So this is to reproduce the experiments that you will see in this movie. And also, it's one thing now, we know that it happens on the ocean. So now it's very recent that we have satellite observations of the swell propagating across the ocean. So here it's the Pacific Ocean. And so you see that so the color is the wave height. So the red is relatively large waves. But what you see is that these wave systems do not just go straight. Then sometimes, they change directions. And so you can imagine that sometimes they collide. So let me... So that's the, it's one of the nicest wave tanks in France. So the waves are generated by a wave maker which has about 30 panels, and they can be programmed independently. And here the idea is to give a motion that will produce some focusing of the energy in the middle of the tank. So this is essentially a linear phenomenon, at least at the beginning. You decide where you want to focus the energy, and then you can program your wave makers, and then that's what you get. So very effective way to create a big wave. Okay. So now we switch to nonlinear mechanism, the modulational instability. And so this one is very important because that's where the link with the optics is. So what do we mean by this modulational instability? If you take an initial wave condition, which is a monochromatic wave, with a small disturbance added, and this disturbance is a modulation with a wavelength which is much larger than the wavelength of the carrier. So sometimes it's called a long wave modulation. And after several wave periods, instabilities develop. So this is the initial condition. So actually here you have a bunch of sinusoidal waves in some sense. And then energy becomes concentrated at a single peak in the wave group. Now, strictly speaking, there is a recurrence phenomenon. So then this occurs, and then it will disappear. And this is a blow-up of this region. So you have these waves with about the same height, and then you have this big peak that comes into the picture. So I was in Novosibirsk yesterday, and there was a conference organized within the framework of the mega grant of Professor Zakharov. So you see, it's okay. So now, of course, to work, these illustrations are based on the full water wave equations. But as I said, it's difficult to compute waves using the full equations. I mean, it's done, it can be done, but if we want to go something quicker, then there is a very nice model for water waves, which is the nonlinear Schrodinger equation. Now, of course, it's called the nonlinear Schrodinger equation, but it has nothing to do with Schrodinger. But still, here I just illustrate the, Schrodinger has a close link with Ireland. And actually in 1938, the Prime Minister of Ireland was planning to establish an institute for advanced studies in Dublin, like in Princeton. So actually now it's called the Dublin Institute of Advanced Studies. So it's the same as my name. It's Dias. So the Prime Minister wanted an eminent physicist to head the School of Theoretical Physics, and that's how Schrodinger came to Ireland. And actually, just a few days ago, when I was coming to Russia, I was reading the Irish Times, and there was an article on Schrodinger again. And so this article was saying that Schrodinger stayed in Dublin for 17 years, a period he described as the happiest years of his life. So, this is some advertising for Ireland. So, now, the nonlinear Schrodinger equation is the simplest approximate equation that describes the modulations of weakly nonlinear deep water gravity waves. So you take, in some sense, a sine wave with a wave number k, a frequency omega. That's the depth, water depth, vertical dependence. And then that's the amplitude of the wave. And then this amplitude is allowed to vary slowly in time and slowly in space. And then plus the complex conjugate. So after a little bit of work, you can find the equation that governs the evolution of this amplitude, and that's what is called the nonlinear Schrodinger equation. So which is written here for water waves. C sub g is the group velocity of the waves. And so what do we have? We have this cubic term here, and then we have this dispersive term. So we have the same in optics. So actually the nonlinear Schrodinger equation is also used in optics. And actually, so if you use this transformation, you can transform it into a canonical form, which is this one here. So the time derivative, the double space derivative, and the cubic term here. Now, and so this Benjamin-Fehr stability, modulation and stability, is that a monochromatic wave, which is perturbed by a modulation with n waves in it, will grow. It will grow, and then it will return to its original state. Now, you will see the equation both in optics and in water waves. That's the equation for water waves. In optics, this is actually space, and this is time. So actually, in optics, we'll have I will use a xi here and a tau. But then it's a subtle issue, so you have to be careful when you compare the results. But also, if you use the nonlinear Schrodinger equation in a wave tank, actually you can show that it becomes the one used in optics. So there is definitely a similarity between the two. Now, the nonlinear Schrodinger equation is simple, but it's very rich. And again, even today, people are still writing papers, mathematical papers on the nonlinear Schrodinger equations. And I'm not going to talk about all the explicit solutions of this equation. But here, I will emphasize a few of these equations. So here's Zhenya Kuznetsov, and there is a solution actually named after him, the Kuznetsov soliton. And so that's an illustration here. Now, that's an exact solution for A, the amplitude, but remember that the amplitude is multiplied by the carrier. So actually, that's the Kuznetsov soliton And then, of course, it's multiplied by this oscillating function. So the wave signal is this, and then the wave increases, and then it decreases again. So you start seeing this type of formation of freak wave. And actually, if you look at here, you have only one big wave, but you can easily imagine that depending on the oscillations underneath the envelope, you can have 1, 2, 3 waves underneath the peak. Now, there are some, so these solutions, like this one, it's called a soliton on a finite background, because the amplitude does not go to 0 at infinity, it goes to a constant value. Now, of course, for the Schrodinger equation, there are some solitary wave solutions, but there are pulses on a 0 background, so they go to 0 at infinity. And then there are also some periodic growth decay solitons or breathers. So sometimes they are called the Akhmediev breather. And so now this is a picture taken from optics. So now that's the distance xi and the time tau. But so you have these, so these peaks breathe in time. So they appear and disappear. And then, if you take the limit of this solution, when the period between these two peaks goes to infinity, then you get this very nice analytical solution, which was first discovered by Howell Peregrine. So we call it now the Peregrine soliton. And it's a very simple expression, it's algebraic. So again, x and t, and it's just a single peak. So remember what I said at the beginning for Rogue waves, localized in space, localized in time. So this could be a good candidate for this. So then, so now I'm jumping to optics. So since in optics, in lasers, you have both dispersion and nonlinearity. People in optics use the nonlinear Schrodinger equation, so this solution is also a solution for people in optics, but it had never been observed in the past. So, and it all started in, I think it was in 2007, there was a paper in Nature, which was called Optical Rogue Waves. And now, there is a very long story behind this, why, you know, in 2007 people started to realize these things. One thing to realize, I'm not an optician, but working with people in optics, I learned quite a bit. So what was crucial to understand the emergence of these extreme events in optics was actually the discovery of the supercontinuum. And actually this is an illustration here. So it's essentially, you know, you start with a narrow frequency and then you end up with white, so a very broad spectrum. So, and actually this was discovered recently, and actually the people who discovered the supercontinuum got the Nobel Prize. And that was not that long ago. So this is important to realize too, that even 20 years ago, you know, people wouldn't have been able to do these experiments. But actually what happens is, well, this is 3 types of spectra obtained in optics. And the difference is the power. So that's a small power, intermediate power, and large power. And actually the one we are interested in is not this one. It's this one, where actually you get a breather regime, the Akhmediev breather that I just showed. So there is a very good comparison between, I will show it, numerical results, analytical results, and experiments. And then here, it's actually the spontaneous modulational instability sidebands. So you start, you have the growth of these two sidebands. But in some sense, this is the beginning. So these sidebands grow, and this is in some sense the nonlinear continuation of what happens. Now, I like this quote by Lighthill. So fluid dynamicists were divided into hydraulic engineers who observed things that could not be explained, and mathematicians who explained things that could not be observed. So this peregrine soliton was definitely an observable soliton until recently. So first, that's when I started to work with people in optics. And so first, by understanding each other, we made some progress, and then they designed some experiments to get these Akhmediev breathers. So for example, this is the experimental results, and these are the analytical results with the red dots. And so here is again the same equation, except maybe that the one I wrote before was with the factor 2 here, but it doesn't matter. And so this is this exact solution, the Akhmediev breather. And actually you will see that it depends on only one parameter. It's the A, which is given here. And you see that there is a square root here of 1 minus 2A. So actually these solutions are for A between 0 and 1/2. And actually the peregrine soliton is the limit of this solution as A goes to 1/2. And actually when A goes above 1/2, you get the Kuznetsov soliton. You get the other one. So what happens if you go beyond 1/2 for A, well, you see right away that well, the B becomes complex. So actually you have to change the sinh into sines, and the cosines and sines into cosh. And so these are the two, one is the Akhmediev breather, the other one is the Kuznetsov soliton. So, as I was saying earlier, I'm not saying that doing experiments in optics is easy, but experiments in optics can be done in a relatively small room with quite a bit of equipment, and it can be repeated over and over. So it's easier to vary the parameters to understand what happens. So then the next step was to try to find the peregrine soliton experimentally in optics. And so that was a paper 2 years ago in Nature Physics. That's I will not go through the description of the experiments, except that there are two coupled lasers. And then this is a comparison between the experiments, the circles, the analytical solution, and the numerical simulations. So a pretty good agreement. Something interesting too is that at this point there is a phase drop of pi. So in the theory it's actually a jump of pi, and then in the experiments it's a very sharp decrease. So, okay, so that was in optics. So we had the paper in 2010, and then a few months after that it was published. Then there was another paper by a team in Germany, which was rogue wave observation in a water wave tank. Now, again, why? So I will go through this paper and the results, but this was a year ago, May 2011. So why did it take so long to get this? Well, the reason is that this modulational instability, I told you it's a long wave instability. So actually, you need some space to develop this instability. You cannot do it in a small wave tank. So, and then also it's better, to use a small wave height. because if you use a large wave height, then you would end up, you need a 200-meter long wave tank or even more, and so it's not very practical. So what they did is, where they were not afraid of using small waves, you will see the experiment in the next slide, in the next movie. But what was really amazing is that they said, and nowadays, with wave tanks, you can prescribe almost, exactly the wave you want at a given point, and then it will propagate, of course, if the theory is correct, it will propagate the way theory predicts. So essentially, we have an explicit solution here, and they essentially entered the wave they wanted at a given point in the wave tank. So for example here, that's the signal they put, so with the little perturbation. And then this is the propagation along the wave tank. And so the instability develops, and actually you get this rogue wave here. That's a blow up of the solution. So actually in this one you have 3 waves, 3 large waves in some sense. Now, I have guessed the wave amplitude. Of course you cannot see it because it's very small, so I circled it. That's 2 centimeters. Here, so there is one thing that I didn't show. It's that among this family of solutions, that's the one with the maximum contrast. And actually, if you compute the amplitude at t equals 0 and x equals 0, you see that you have 1 minus 4. So you have a factor 3. So actually, the background, if the background is at 1, the height here is 3. So actually, here, that's 6 centimeters. So that's, you have a 2 centimeter wave, and then you get a rogue wave of 6 centimeters, but it's according to the definition, it's a rogue wave. So now so that's the experiment in Germany. So that's the wave tank. And then, to study the damaging effect of the wave, there's a little Lego boat in the middle of the tank with a cannon. So I don't know who is in war here, but so that's the 2 centimeter wave that is propagating nicely along the channel, but this noise has been added in some sense. Here it comes. So it's going to hit the boat now. So what's going to be the effect? And that's it. So that's the rogue wave that made the boat capsize. Now I just want to show, since I'm here, 2 other animations. So I will play it again. Now this is, this one parameter family of solutions I showed. That's the effect of changing this parameter A. So, I will play it again. Now we're on the Kuznetsov soliton regime. And actually, when A becomes very large, in the limit, we get the soliton solution. So I play it again. So we start with A equals 0. And so this is the Akhmediev breather. So actually it's periodic in time. And then the period, that's the peregrine soliton, and that's the Kuznetsov soliton. And so as you increase A, then the period becomes smaller. And now this is the last movie. That's the experiments in optics done in Dijon. So this is, so first it was the Archimedes breather. So, and then that's the, this extreme event that is generated. Now, so when it goes down, you see that it does not go back to what it was. And actually what happens, in optics there is some third order dispersion, which is also important. Now that's the spectrum here. So that's the evolution of the spectrum. So it looks like what I showed in the picture. So yeah, when it goes down, there are some other effects that come into the picture. And now that's the peregrine soliton. So the formation of this extreme. So I think the theoretical limit is 0.5 for A, and so they managed to come to 0.47 in the experiment. So again, this split, when it goes down, it's a third order dispersion effect. So, and I think, yeah, that's, I think, yeah, I'm finished now. I had left some mathematics for after, if there was some time left, but I will stop here.
Your solution for Nonlinear Schrodinger Equation is unidirectional or bidirectional? Unidirectional. And what is more important, rocky wave crests with high crests or rocky wave as a high trough, deep trough? What
That's an interesting question, because there are a few. So in this catalog, a few are more big troughs than big crests. So it's true that we emphasize the big crests, but the big troughs are also very important.